our speaker, the first speaker for today, all the way from Johor, all the way from Johor, live streaming from Johor. So he is currently a senior lecturer from UTM, University Technology Malaysia. He obtained his PhD in 2016 from UTM as well. He has experience in handling high advanced instruments such as TEM, SAX, SEM, etc. And he also has published his work in ISI, WS, Corpus, and has numbers of collaborators from industries and universities. And he also has secured national, both grants at national and international level, as well as currently supervising a number of postgraduates in UTM. And currently, he is the head of Green Chemistry Research Group in Faculty of Science, UTM. So his expertise or research areas is in supramolecular chemistry, metal organic frameworks, chemosensors, color tunable materials, nanomaterials, material characterization, polymers engineering, nanomaterials synthesis, and also nanostructured materials. So I think without further much waiting, could you please use the reaction button as soon as I welcome our first presenter for today for 30 minutes, Dr. Juan Matmin. Could you please give him a big applause?
Hello, hi everybody. Thank you.
Welcome, Dr. Juan. Hold on, let me just stop sharing. Okay.
Thank you, Yati, for the nice introduction.
Welcome.
Please allow me to share my content.
Your webcam okay?
Boleh lah. So.
Okay, all right.
Okay, can everybody see my slide?
Yes, we can see it. Oh, not yet. It's just blank space. Okay, now we can see you. The slide.
Okay.
But still no webcam. You don't want to, or maybe the bandwidth is not good.
I think I prefer disfigured.
You want to remain that way? Okay, never mind. I'll just be here. Okay, proceed.
Alright. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good evening. Good afternoon, good day, everybody. Right. My name is Juan bin Matmin. I'm currently the head of Green Chemistry in Department of Chemistry, University Technology Malaysia, all the way from Johor Bahru, as Yati said. Okay. The need for green approach is inevitable. Okay, because this is dealing with the energy. So energy will never be enough. Therefore, the energy is based on fossil fuel dependent will be in the end deflect. This contribute to serious issues such as global warming, high energy consumption, and therefore we in UTM established a research group known as Green Chemistry. These are group with special initiative to establish the work that emphasize on green approach, okay, for development of novel material. These are the wonderful people behind Green Chemistry. Okay, there are people that are in different backgrounds, right? Such as Dr. Afiq, he is the expert in forensics. Dr. Sazwan is expert in organometallic. We have Dr. Sheila, expert in photocatalyst. We also have Dr. Susila, who is expert in energy material. We have the Dr. Siti Aminah, who is also expert in surface and colloid. We also have Dr. Fazira, expert in computational chemistry. The newly joined members is Dr. Hamdi, who is the expert in biotechnology and drug delivery. Okay, so we are welcome on any collaboration from other units or students who would like to ask anything based on our expertise. Okay, so don't worry, we are here to help you, and tak payah nak malu lah, just tanya je kalau ada apa-apa, just inform us. If we can assist you, we'll be happy to do so. let's go back to the topic that we are currently interest in. Okay, so today's topic is basically about nanomaterial. Okay, this nanomaterial is based on the size of material that are from 1 nano to 100 nanometers. Okay, so there is a small area or range dependence there, which is this material have a specific or unique properties that need to be fully understand and characterized, because there are several what we call as consideration, especially when we talk about the size distribution, shape, and the surface area. In this nanomaterial also, we have to consider the structure. Okay, how this material form, where there is a zero dimensional, which is usually a course-shaped cells, okay, particles, or a sphere. Okay, so these are the zero-dimensional material. But there is also a one-dimensional material, structured material known as carbon nanotube, which is very popular in the biomaterial science. And we have also arrays, okay, array material. For the two-dimensional materials such as graphene, okay, very famous in the energy storage research. We also have the carbon based material, carbon coated material. This is known as a two-dimensional layered material. We also have a three-dimensional material such as mesoporous composites. Okay, we have the hexagonal structures there, the rafter shape. We have also a mesoporous composite with a channel there, how to determine the channel. We have also the composite, which is usually used as an electron. So the world of nanostructured material composed of very unique material as what I highlighted earlier, and this material usually have the ability to manipulate itself within the range of size from 1 to 100 nanometers, and this material is also have a higher specific space area, which is currently or usually have been developed as an advanced material. These are the characterization methods for nanomaterial. Okay, usually when we talk about nanomaterial, when we want to determine the size, we always depend on the dynamic light scattering. This is going to give you a size and the size distribution. I'm going to talk, focus more on the microscopy part, where I will be discussing or sharing part of my knowledge in the transmission electron microscopy, scanning electron microscopy. This is where we have the what we call as the size and morphology. Okay, so we are going to discuss further what is morphology, and there is also a bonus for you. I'll be discussing also on AFM, atomic field microscopy. So that's will be covered again. So let's look how we can characterize this material. Okay, the first thing, as mentioned, when we talk about structured material which is in a specific size, okay, we usually depend on the dynamic light scattering, or DLS. Okay, this DLS usually require you to do analysis, okay, to do analysis in the suspension. So this technically is highly dependent on the measurement of speed of the particle undergoes a Brownian motion. So when we are able to measure the Brownian motion, we are going to see how the particle size or the viscosity going to be look like. So this is the theory of the Brownian movement. Okay, colloidal sample or suspension usually move around in an erratic and random motion. So this letter going to give a relation in terms of particle size, viscosity, and not to forget the temperature as well. So this is how we depicted our Brownian motion. This is random and erratic, and we are going to able to measure this based on the light scattering and having a certain derivation of mathematical equation. We are going to able to determine the what we call as the hydrodynamic science. So this is what we look on the hydrodynamic science. Okay, this is not what we call as a real science, but the overall size of the particle or the material. The overall size of material in let's say you are developing a quotient material, you are not only going to have the particle, but things that is coated outside the material. Let's say you are developing a particle that is highly agglomerated. So the hydrodynamic size going to be measured as a aggregate. Okay. But the dynamic size there going to include all the aggregation here and give you a spherical shape. This is usually difficult for sample with morphology of a non-round shape, such as oval shape, layered material. That is very difficult to be measured. But in the end, we have to understand or know that DLS is measuring based on the hydrodynamic size, because we usually refer this material as a sphere shape. Okay, so that is the approximation based on the mathematical derivation in this DLS. So how DLS can contribute to your work? I think this is the interesting part that everybody would like to know. Okay, this is the work published by my group and I, and with the collaboration of company known as IPS. We also have a collaboration with Sympatec in Germany. Okay, there is one guy known as Daniel Werner coming all the way from Germany, and he would like to promote his DLS. Okay, if you have came to know that DLS is famous for its brand known as Melbourne. So in this case, that Mr. Werner come to me and asked to promote his model of the LS in order to penetrate the Asian market. So we have published this in nanomaterial with a good impact factors and a Q1 papers. And this is a result from the DLS. Okay. I have a material known as thin disulfide here, which is highly agglomerated, and this material have a difficulty in understanding how it's distributed. So I discussed with Mr. Werner and give him this sample, and alhamdulillah we got the result based on his measurement, okay, which is instrument. We got the particle size of around 870 nanometers, and the binomial distribution around 0.3 to 2.9 micron. So let's relate back to the microscopic characterization that we are going to be focused on. So this result based on the binomial distribution on the DLS is in good agreement with the heat transmission electron microscopy. Let's take a look on this result here. This aggregate captured or being measured by the TEM micrograph shows that this aggregate giving you a size of more than 500 nanometers and composed of a large number of nanosheets. This is in good agreement with the LS. So I'm happy that based on our collaboration with Sympatec Germany, we are able to publish this paper. And not only that, we also support this organization. To take a look at, we have the measurement based on the LS earlier. We support back with the TEM, and we support with the FSAM. And this material is actually consists of layered material. and is highly aggregated. That's why it's make an average distribution of around 800 nanometers, which is in agreement in a good agreement with the DLS and DEM. Not only that, after that, we propose a plausible mechanism on how this material form, because we want to emphasize the green chemistry approach using the photochemical synthesis. So this is how we propose a mechanism based on the result of DLS earlier, DEM, and then PSM. But before you venture or send your sample for measuring DLS, these are some considerations that you need to understand. When we deal about using DLS, of course, the measurement will be fast and very small quantities of sample can be used, but the sample is usually doesn't produce a good resolution of the histogram, and it's difficult for you to obtain the information of shape. That's why we need the help of microscopy approach. And there is also limitation in terms of scattering effect. If your material is absorbing light sample, so that will be a bit difficult. And also take consideration that you have to be very careful on preparing your sample lab. That's why we ask the help from the expert, because it's usually contaminated by dust. So these are things that you need to consider. When let's say you have a sample and your supervisor asks you to do a measurement, make sure you find the right instrument that you would like to characterize, or what are the information that is really necessary for you to make your sample to be analyzed with the instrument. That is the first consideration that you have to understand. Okay, and take note, as mentioned earlier, DLS have the limitation of a true particle size. It's only giving you the measurement of the hydrodynamic radius, and you're also going to get a low resolution of sample, provided that the sample here are closely populated, meaning that highly aggregated sample will not giving you a precisely measurement. That's why in our result earlier, we found that the distribution of sample is around 800, but when we look at details based on the DEM, it's actually around 500 nanometers only. So that is why we always have to counter back and check and confirm our measurement. Okay, so when we talk about microscopy technique, some of the optical microscope, okay, usually we refer to optical microscope, especially when you deal with the clinical samples, biological sample. You usually only look at the optical microscope, but this is not suitable for nanoscale analysis because the resolving power is very limited. It's around 250 nanometer, but the material that when we talk about nanomaterial is around 100 nanometers. So in the end, if you try to look at the sample using a simple optical microscopy, you will only have a blurred and undistinguished sample. Therefore, we tend to have an alternative of this, which is an advanced electron microscopy. Okay, there are two types of advanced microscopy. One is DEM, which is going to allow you to study on the inner structures, and we also have the scanning electron microscopy, which we use to visualize the surface of the object. Okay, let's take a look a bit. I'm not going to go detail on the technical part. Okay, we are going to look on how the SEM, scanning electron microscopy, operates here. Basically, the detection methods consist of secondary electron. We also have a backspin electron and X-rays for determining the composition. Okay, and how we are going to get the micrograph image. Basically, when we have a sample based on the detection method earlier mentioned, is going to give you a part by part image. Okay, so we scan on a part of the image. So we make an micrograph here, the sample image here, one part, and this image is going to be arranged part by part, like you are playing a jigsaw puzzle. Okay, so you play. In the end, you are going to have a overall image based on the lines and the points that you scan on the specimen. But in order for you to able to have a good image or micrograph image, you need the vacuum system. Okay, SAM is based on the optical column and the sample chamber, which must always be kept in vacuum. This is in order for you to reduce the beam intensity or the instability of a sample. So that's why we need the sample to be vacuum, and we have to do a sample preparation before that. If the sample is not really well prepared, and you have an interference within the sample chamber, you are not going to have a good contrast of your micrograph image, which in the end your image will be obscure. Okay, this is what I mentioned on the sample preparation. First of all, your sample must be clean and completely dry. That is the first consideration. Okay, don't send a sample that is already exposed in air for overnight. So you have to dry the sample first, or better still, you can outgas the sample or vacuum it. The sample must be dirt removed, and also most importantly is going to be coated, okay, to make it conductive. Okay, so there are several ways or coating protocol that you can look at, but the most common one is using the sputter coater. Okay, this is a sample of a spider that we coat on the gold, and the sample usually placed on the 13 millimeter radius of aluminum stud. And here we are going to place the sample here, and then we sputter it with the metal coatings. So how SAM can contribute to your work? This is interesting. Okay, as mentioned in the first example on how I use the DLS and supported with the TEM and the SEM, we are able to get a good image of a layered material. In this case, we propose a new preparation method, which we find as a direct continuous preparation method using a rice starch templated method. Okay, in this study, we use SAM micrograph image to display a transformation process. Okay, remember that this paper discussed on the rice starch template. So we want to what we call as pictured or captured the image of the transformation process of starch. Okay, this is rice starch. It's in its granule, and this is the effect of water that undergo a gelatination process. This is where we have the sol-gel process of the sol-gel rice starch template. Okay, and in the end, this is the material that we are looking at, or the silicate nanostructures. Okay, so this is contribution of SAM in displaying the morphological synthesis. Okay, we can not only have a simple micrograph image of a final product, but we can follow the transformation of a synthetic process, a new process that we propose. So in this paper, we also proposed a plausible mechanism how the rice starch act as the template in the new protocol here, and this follow the image of the PSAM that we measured. Okay, these are the advantage of the SER. Although the instrument work very fast and allow generation of data in the digital form, it's also good because the sample only require a very minimal. But not everybody can use or conduct or operate this instrument. Okay, only well-trained people that know how to prepare and have a good knowledge in handling this instrument, know where to have a good spot of the image. So if you are untrained, you might have a good sample preparation, but in the end, you've got a very bad image. That is also very disappointing. And this usually for the SAM, in conventional method, only able to measure a solid sample, but it's not always true because I have myself measured a liquid sample, but we need to have a further treatment. As mentioned before, the sample being able to measure, if you are going to have a coating, okay, surface coating there. But in the case of gel or liquid sample, you have to know how to make what we call as operate a cryogenic sample. Okay, so you can operate, then freeze the material in the liquid nitrogen, and in the end you are able to measure a sample whether is it in liquid or in gel. Let's talk on the transmission electron microscopy. This is a high-end unique instrumentation where we can not only measure the micrograph image, but we can also have the information of the crystal structures and the diffraction, which is in combination for the diffraction and the imaging techniques. Okay, so this is a bit on the operational techniques. It's operate on the electron pulses because of the wavelength characteristic, and it's usually measured the inner structured sample by penetrating on the sample of a several micron from the surface. So the difference between SAM and TEM, SAM, let's say you are going to take a picture, only show what is your face. You all love to make a selfies. So when we talk about SAM, the face there is going to be captured using the SEM. But when we talk about transmission electron, as an analogy, we're actually looking at far deeper behind your skin or perhaps your skeleton. Okay, mungkin nampak gambar tengkorak lah ini, and we operate using the TEM. Okay, these are the sample chambers. Take note that the imaging system here is rely on the electromagnetic lens and the also the phosphorescent screen, meaning that this instrument operate based on the electron beam, and of course you need a sample vacuum as well. But not only that, the instrument required what we call as frequent maintenance. Okay, so these are the different modes. Okay, these are the different modes in order for you to have a different obtain a different information. In this case of a bright field sample, perhaps you are going to able to have the information of the diffraction. If we want to have a different mode, so these are the different modes. We have bright field, on off axis of a dark field, and both combination, either the bright field or light field or dark fields. Okay, so that's different modes depend on the operator expertise, you actually going to have a more than just an micrograph image. Let us discuss further. Okay, how time can contribute to your works? Okay, already touched on the SEM, so let's look at how time can contribute this in your works. Okay, this is a paper published by my team and I. Still based on the green chemistry approach, okay, still on the rice starch synthesis, but in this case we are looking at a spherical shape of a nanostructured hematite. So we are going to prove that this material is actually spherical, and we also are going to see whether the hematite is actually a nanostructure. So this is how we use our manipulate tank to determine the hematite exists there. First of all, based on the high energy electron diffraction, we know that according to the Bragg law, this is going to give you a diffraction pattern. So the diffraction pattern of each metal is going to be constant. So each metals, okay, either is iron, either is nickel or what, you are going to have a similar diffraction pattern. So this is one good indication or confirmation that this material is based on selected metals. In this case, it's hematite. And based on that, we are going to look on the crystal lattice and based on the d-spacing as well. So the d-spacing here contribute to the 0.25 nanometer, which is common, is small for hematite. Okay, this is very true for the hematite. And when we look at the photographic image here, you know that these particles are corresponding to the hexagonal structures. So based on the tank, take note that it's not only on the image. We are going to learn on the crystal structures, where a crystal structures giving you a spacing, the orientation, the spacing here. So based on the d-spacing, we can confirm that this material are hematite because the diffraction there can be indexed to a GCPDS number. And take note that this is in good support with the TEM based on the lattice and the crystal structures. So in this case, we are going to compare the SEM and the TEM. Take note that in the case of sample for the SEM, sample here must be conductive, or you have to at least code it. For the TEM, the sample must be thin enough to be coated on the carbon mesh, right? So using both characterization analysis of the SEM and the TEM and how this can contribute to your works. In this case, we are going to prove that the material is oval shape there, or spherical shape. So we use the SEM, and then we compare this image with the TEM image, and we found out that this is true for the hematite structures, and we further analysis with the image J analysis. This is can be freely downloaded. It is a free software developed by the researchers from Oxford, and you are able to have a surface plot to support this material is actually a spherical shape. And then based on the SEM and TEM observation, we propose a specific possible mechanism based on the nature of our template. In the case here is a starch, so there are specific interaction of a different process. As mentioned, we already looked at on how the starch transform, and then there is a specific different metals that we look into it, and this this case of hematite, this follow a different scheme, follow as a granular scheme, then integration step before it's being calcined. So as a bonus for today, okay,
sorry to interrupt, Dr. Juan. 3 minutes left. Okay, thank
3
you.
minutes.
Yeah, 3 minutes. Thank you.
Okay, last point to be taken home. I'm going to touch a bit on the AFM. Okay, AFM going to give different type of morphologies. Okay, so this is not on. This is how the operational principle look like. Okay, and it's highly dependent on the tips. Okay, so I'm not going to go for the technical part. This is different mode. Either you are going to have a contact mode, different contact mode, or non-contact mode. And the advantage, okay, I would like to highlight the advantage of a AFM. Okay, how AFM can contribute to your works. We just recently published a works in electrochemical acta, okay, and in factor with 6.16, a Q1 papers, and this actually deal with the biopolymers. Okay, so we use AFM to determine the 3D structures of the biopolymers. Okay, so this is incorporation of our morphological analysis based on the SEM and the AFM. So okay, let's take a look on the pictures. For SEM, you are only going to have a 2D image, but for AFM, we can know a 3D image and advantage of your z-axis or the depth analysis also. So that is the main advantage of the AFM. So this is the comparison of our AFM SEM and TEM. So for AFM, you can know the 3-dimensional analysis. That is good if you have a material that is consists of a different layers material. Okay, this is work in a biomaterial comparison of SEM, TEM, and AFM for peptide. Okay, let's come to the end. Let's wrap up things. Okay, so in order for you to understand your material, you have to be able to analyze in depth using various instruments. Okay, let's say your supervisor wants you to characterize this material. Make sure you are able to correlate this result into each other. Okay, it's not going to stand alone. So you must able to correlate the measurement there and the analysis. And in the end, please remember to propose something in order to establish the result correlation. That is things that you have to able to understand in doing your research. Okay, I'm not the expert of everything. You are the expert of your own field, and you know what you are synthesizing in, and I wish you all the very best. With that, I'd like to say thank you.
Thank you very much, Dr. Juan, because we cannot, okay, we cannot see you just now. So yeah, thank you very much for a very informative talk.